Okay, let's unpack this. We're seeing this explosion of AI-generated text everywhere. It's pretty amazing, right?
It really is. But it brings up that big question.
Yeah, how do you actually know if you're reading something from a person or a machine?
Exactly. And that's where watermarking comes into the picture.
Right. And today we're doing a deep dive on one specific type.
Yeah, a really important one. Statistical watermarks. These are fundamentally different, from the simpler stuff.
Like hiding invisible characters, zero width spaces, that kind of thing.
Precisely. Those methods, well, they're often pretty easy to strip out.
You just find the weird characters and poof, they're gone. Seems brittle.
Totally. Statistical watermarks are way more subtle. They don't just add stuff after the text is made.
Okay.
They actually influence the AI's choices as it's generating the text. The signal isn't some hidden symbol.
It's more like a pattern.
Exactly, a hidden statistical pattern that's woven into the probabilities of the words the AI picks.
Ah, okay. So for this deep dive, looking at the sources you've pulled together, our mission is basically to get how these clever statistical watermarks work.
Right. How they work, how people try to detect them,
Right.
how tough they are against removal attempts.
And why getting rid of them is apparently much harder than just deleting invisible characters.
That's the core of it. We'll look
Yeah.
at the mechanisms, the detection, the whole attack landscape, robustness, and the sort of bigger challenges.
Okay, sounds good.
Yeah.
Let's start right at the beginning. How does an AI even generate text? And then how does a watermark get slipped in there?
Good place to start. So think about a large language model, an LLM. It basically predicts the next word, or token, right?
One after another.
Yeah. Given the text it's written so far, it calculates these raw scores, they're called logits, for every possible next token in its huge vocabulary.
So it's like scoring all the potential next words, thousands of them.
Tens of thousands, yeah. Then these scores get turned into probabilities, usually with a function like softmax. And finally, there's a sampling step that picks the actual next token based on those probabilities. The statistical watermark interferes just before that final sampling step.
Interesting. So it's actually messing with the AI's decision process.
Messing with is one way to put it. It subtly modifies the logits, or maybe the probabilities, before the model chooses the next token.
Oh.
It uses a secret key and often the preceding text, the context, to guide this modification. By doing this over and over, token by token, it encodes a signal.
A signal in the sequence of words chosen.
Exactly. And the idea is you reading it shouldn't notice anything strange, but someone with the key and the algorithm can statistically detect that pattern later.
Okay, that's clever. Let's get specific. The KGW method, Kirchenbauer et al. That seems like a really foundational one. How does their green-red list idea work?
Right. KGW is key. It uses something called a pseudorandom function, a PRF. Think of it like a recipe. It takes the text just before the next word, the context, maybe the last few tokens, and a secret key. Using that specific context and that key, the PRF splits the entire vocabulary into two lists for the next word.
A green list and a red list.
Exactly. And it does this deterministically based on the key and context, but it looks random if you don't have the key.
So, like, for this specific spot in the text, apple might be green, but banana is red.
Could be, yeah. Now, the main KGW trick, sometimes called so promotion, is simple. It adds a little positive bump, a value called delta, to the logits of all the tokens on the green list.
Just boost their score slightly.
Just enough to make them statistically more likely to be picked than they would have been otherwise.
So it's not forcing a green word, just nudging the odds.
That's the critical point. It's a statistical tilt. And this leads directly to that really important trade-off the sources mention, the entropy dilemma.
Entropy, meaning uncertainty, like how sure the model is.
Exactly. When the model is uncertain about the next word that's high entropy, lots of words have similar probabilities. Adding that delta bias to the green list can significantly increase the chance a green token gets picked.
So the watermark embeds strongly there.
Right. But it might also affect the quality a bit if the model's original top choice was on the red list.
Okay, but what if the model is like 99% sure the next word should be Paris because the sentence is, the capital of France is?
That's the low entropy case. If Paris happens to be on the red list, well, adding that small delta boost to the green words might not be enough to overcome the model's certainty. Paris probably still gets chosen.
So in predictable text, the watermark has less effect on quality because the model ignores it.
But it also embeds very weakly. It's hard to detect later. This is a fundamental problem. You really want a watermark factual, predictable text code definitions, but that's exactly where it's hardest to embed a strong signal without risking mistakes.
That makes sense. It's a tough balance. What about the Google DeepMind approach, SynthID text? Is that trying to solve this differently?
SynthID text, which they recently open sourced, also uses a key and context, but the mechanism's different. Instead of just adding a bias like KGW,
It does something else.
it uses a G function tied to the key to augment the logits, creating unique scores for potential next tokens.
Okay, unique scores. Then what?
Then it uses a process they call tournament sampling. It's not just picking based on boosted probabilities.
A tournament. Like words battling it out.
Sort of. Candidate tokens are drawn, and they compete in pairs based on their augmented scores. There are these little knockouts until one token emerges as the winner. That's the one that gets selected.
Huh. That sounds complicated. Why do it that way? Does it make it harder to remove?
That seems to be the idea based on the sources. It's a more complex multi-step process compared to just sampling from a biased distribution. The link between the watermark signal and the final chosen word is less direct.
Potentially harder for an attacker to figure out or undo without the key.
That seems to be the rationale. SynthID also apparently avoids watermarking repeated phrases, which can help detection, and they claimed minimal quality impact in their tests.
But still acknowledging issues with short or factual text.
Yeah, that low entropy short text limitation seems pretty universal. Like KGW, SynthID is also training free, which is a practical advantage.
Okay, so we have KGW's list bias, SynthID's score tournament, and maybe other ideas floating around focusing on n-grams or other patterns. But that entropy dilemma seems to be the recurring headache.
It really is. Balancing detectability and quality, especially in predictable text, is the core tension for all these statistical methods.
All right, so the signal's embedded through these subtle statistical shifts. But if it's not a visible character, how on earth do you actually detect it later?
Good question. It's not like searching for a specific string, like Cinterol plus F detection is all about statistical analysis.
And you need the secret recipe.
You generally need to know the specific watermarking algorithm that was used, and crucially, the secret key that was employed during generation.
Okay, you have the algorithm and the key. Then what?
The detector basically runs the embedding process in reverse, conceptually. For a chunk of text, it uses the context before each word and the secret key to figure out, okay, if this were watermarked, what should the pattern look like?
Like which word should have been on the green list?
Exactly. For KGW, it would calculate the expected green-red list for each token position based on the preceding context and the key.
And then it looks at the actual text.
And counts. How many tokens in the actual text fall onto the predicted green list for their position?
Okay.
Then comes the statistics. It compares the observed count of green tokens to the number you'd expect just by random chance if the text wasn't watermarked.
Because even random text would have some green tokens, right?
Precisely. If the green list is, say, half the vocabulary, you'd expect about 50% green tokens by chance. The watermark should push that number significantly higher. A key point here is you often don't need the original giant LLM to do this detection, just the algorithm and key.
All right, let's go back to that KGW detection stats test. You mentioned hypothesis testing.
Yeah, that's the standard framework. You set up two competing ideas. The null hypothesis, H0, is, this text is not watermarked. Any green tokens I see are just random chance.
And the alternative.
The alternative hypothesis, H1, is, this text is watermarked. The higher number of green tokens is because of the watermark.
And you calculate a statistic to decide between them.
Commonly, yes. A z-score is often used. You can think of the z-score as measuring how many standard deviations the observed count of green tokens is away from the expected count under random chance.
So a really big z-score means very unlikely to be chance.
Exactly. If the z-score is bigger than some predetermined threshold value, you reject the null hypothesis, H0, and conclude the text is likely watermarked, except H1.
And setting that threshold is a trade-off.
Always. A high threshold means fewer false positives. You won't accidentally flag human text very often, but you'll have more false negatives. You might miss some genuinely watermarked AI text.
Is the z-test foolproof?
No, the sources point out limits. It can struggle with a really short text, just not enough data points for a reliable signal.
Makes sense.
And it can also be less reliable if the text has weird statistical properties that don't fit the test's assumptions. That's why people are looking into more robust statistical methods too.
How does SynthID detection work then? Is it similar?
It uses the key to reconstruct what the expected scores from their tournament process should look like. Then it compares scores derived from the actual text to the expected scores for both watermarked and unwatermarked scenarios.
And they have different detector types.
Right. They mention a trained detector, which might be more accurate if you have data to train it, and a simpler training-free one called the weighted mean detector.
Does it just say yes or no?
Typically, it gives three possible outcomes: watermarked, not watermarked, or uncertain. It depends on where the calculated score falls relative to two different thresholds. Lets the user tune the sensitivity, basically.
Okay, detection needs stats, needs the key. But what about, the real world? Someone copies one paragraph of AI text and pastes it into a huge document they wrote. How do you find that?
Yeah, that's a huge practical issue, the needle in a haystack problem. That small watermarked signal gets totally diluted by all the surrounding human text. A standard detector looking at the whole document might just miss it completely.
So you need specialized tools for that scenario.
Absolutely. This has led to algorithms like WaterSeeker. It uses a two-stage approach. First, quickly scan the long document to find suspicious regions that might be watermarked.
Like a quick filter?
Exactly. Then apply the more computationally intensive detector only to those smaller candidate segments. Saves a lot of time.
Smart. Any other approaches?
Yeah, there are methods drawing inspiration from plagiarism detection tools, things like the geometric cover detector, or GCD.
Geometric cover?
It uses a clever technique with overlapping text segments to very efficiently answer the question: is there any watermarked segment likely present in this entire document? It can be much faster than checking every single possible start and end point.
And then maybe something else pinpoints it.
Right. Algorithms like the Adaptive Online Locator, AOL, can then take that rough location identified by something like GCD and use an adaptive search to zero in on the precise start and end boundaries of the watermark section. These localization algorithms are really vital for practical detection.
Okay, so we've got embedding, we've got detection, even ways to find hidden segments. But now for the million-dollar question. Can people just break it? Can you just edit the text and make the watermark vanish?
Yeah.
How robust are these statistical signals?
This is really where the ongoing battle, the arms race, is happening. Robustness is absolutely critical. The watermark needs to survive changes, both accidental editing and deliberate attacks.
And robustness isn't just one thing, right?
Right. There's imperceptibility. It shouldn't mess up the quality. There's robustness to transformations, surviving, paraphrasing, maybe translation. There's security resisting targeted removal or forgery. And sometimes capacity, how much info it holds, though that's less critical for just detecting presence.
And people are actively trying to defeat them. Is there, research into attacks?
Oh, absolutely. The sources detail a whole range of attack strategies. And platforms like Watermark have been developed specifically to test watermarkers against these attacks in a standardized way.
Watermark. Like a benchmark.
Exactly. It's the first open-source platform for this, really focused on evaluating robustness. And it's already showing interesting things, like maybe simpler, context-free watermarks are sometimes surprisingly more resistant to paraphrasing than context-dependent ones like KGW.
Huh. Okay, so what are the main attack methods people use?
Well, probably the most intuitive and a really significant threat is paraphrasing. Just use another LLM or a specialized paraphrasing tool to rewrite the watermark text.
Change the words, change the sentences.
Exactly. The goal is to disrupt those subtle statistical patterns the watermark relies on. If you change enough words, the pattern degrades.
And does it work well against these statistical watermarks?
Research shows it can be very effective, especially recursive paraphrasing, rewriting the text multiple times. Studies show this can dramatically reduce the detection rate for methods like KGW. Even one round of paraphrasing can hurt the signal noticeably.
Wow. So just getting an AI to rephrase something can potentially erase the watermark.
Or at least weaken it significantly. Because the watermark is the pattern of word choices. Rewriting creates a new pattern. You even see commercial tools advertised specifically for this, claiming to humanize AI text or remove watermarks, basically by doing sophisticated automated paraphrasing.
Even small edits matter.
Yeah, even things like swapping synonyms, fixing typos, or minor rephrasing can cumulatively degrade the signal over the course of a document.
Okay, paraphrasing works, but you mentioned those commercial tools. They often claim no quality loss. How true is that when you're paraphrasing enough to actually remove a watermark?
That's a really critical point, and where the research often contradicts the marketing hype. Yes, paraphrasing tools like undetectable.ai can definitely reduce detectability. The principle works,
Right.
but the studies consistently find that the level of aggressive paraphrasing needed to seriously degrade a robust watermark often does impact text quality. You might see increased perplexity, grammatical errors, awkward phrasing, things that make the text less natural.
So even if a human reads it and says, yeah, that's okay.
It might still be measurably worse statistically or just sounded a bit off. The no quality loss claim for effective removal seems overly optimistic based on the current research. There's usually a trade-off.
Okay, so paraphrasing is effective, but maybe not perfectly clean. What about more targeted attacks?
Yeah.
Like watermark scrubbing.
Right. These are more technical. They try to actually figure out the specifics of the watermark being used, not just blindly rewrite. DMARC is an example aimed at KGW.
What does it do?
It tries to infer the watermark parameters, like which words are likely on the green list versus the red list, maybe the strength of the bias, delta, often by carefully querying the watermarked model itself.
Like probing the model to guess its secrets.
Kind of, yeah. And once it thinks it has a good guess of the watermark structure, it makes very targeted changes, swapping just enough tokens, maybe red for green, to erase the signal while trying to minimize changes to the overall text.
Trying to be more surgical than paraphrasing.
Exactly. There are other methods too, like B4, which uses optimization techniques to find edits that reduce the watermark signal while keeping the meaning similar, or SCTS, which tries to guess token colors based on frequency and then makes substitutions.
These sound harder for an attacker, though.
Definitely harder than just running a paraphrasing tool. They often rely on being able to interact with the model or having some knowledge of the potential watermarking scheme. It really underscores why keeping the keys and algorithm details secret is important.
Okay, what about spoofing? This sounds bad. Can someone make nasty text look like it came from a legit watermarked AI?
This is a really tough one, and it exposes a fundamental dilemma. Piggyback spoofing is the classic example.
How does that work?
An attacker takes some genuinely watermarked text. Then they edit it significantly, maybe adding misinformation, toxic language, changing the whole meaning, but they do it carefully, specifically trying to preserve the original watermark statistical signal while making their malicious changes.
Whoa! So the harmful text would still get flagged as watermarked.
Potentially, yes. If the watermark is designed to be robust against edits, which you want so people can't easily remove it, then it might survive these malicious edits too. And then the detector says, yep, watermarked, potentially blaming the original AI source for the harmful content.
That's a serious catch-22. Robustness against removal makes it vulnerable to spoofing.
It's a core tension highlighted in the sources. Designing a watermark that is perfectly robust against removal, but also fragile enough to break when the meaning is maliciously altered, that's incredibly difficult. They work against each other.
Wow. Okay, one more attack vector.
Yeah.
Can attackers misuse the detection process itself?
Yes, absolutely. If there's a public detection tool or API available,
Like an online checker.
right, attackers can use it as an oracle. For removal, they can paraphrase or edit their text, check it with the detector, tweak it again, check again, repeat until the detector says, not watermarked.
Using the detector to guide the attack.
Exactly. And for spoofing, they can craft their malicious text and keep tweaking it until the public detector says, yep, watermarked. It helps them fine-tune their attack.
Can they find out if a watermark is present even without the key?
Some research suggests that might be possible, yeah. Maybe by analyzing how the model generates text under certain conditions, you could infer the presence of a watermark, even if you can't read it or know the key. Just knowing it's there could help an attacker choose their strategy.
So, considering all these attacks, especially how effective paraphrasing seems to be, how realistic is it to completely remove a statistical watermark? Can those online tools really deliver undetectable AI text?
Again, it's that gap between the marketing claims and the technical nitty-gritty. Paraphrasing tools can definitely lower the detectability score, sometimes significantly. The core idea of disrupting the statistics is valid.
But the quality hit is real.
The research strongly suggests that for the level of paraphrasing needed to truly make a robust watermark undetectable, there's very often a measurable hit to quality, fluency, or coherence. No quality loss is probably an overstatement for effective removal. It's almost always a trade-off.
And the targeted scrubbing methods, like the mark.
They might offer a path to removal with less quality damage if they can successfully guess the watermark parameters. But that guessing process itself is hard, maybe expensive if it requires lots of model queries. It's a higher bar for the attacker, and again, keeping keys secret helps defend against this.
So is total guaranteed removal feasible?
The consensus from the sources seems to be that removing all traces of a well-designed statistical watermark without significantly damaging the text's quality or meaning is extremely difficult. Remember, it's a distributed signal.
Not just one thing to erase.
Exactly. You'd likely have to change a large fraction of the text. And newer watermarking schemes are being designed with robustness against known attacks in mind. So removal is often more about getting the signal below the detection threshold, not achieving perfect erasure. It's very much an ongoing game of cat and mouse.
Definitely sounds like it. Okay, beyond specific attacks, are there more fundamental limits or practical challenges this whole approach faces?
Yeah, there are some deeper issues. People talk theoretically about unremovable watermarks, maybe embedded deep in the model weights themselves, so removing the watermark actually breaks the model's performance.
That sounds powerful.
It does, but turning that theory into practice faces major hurdles. It often relies on strong assumptions about attackers that might not hold up. Truly unremovable watermarks seem mostly theoretical for now.
And those inherent trade-offs we keep mentioning.
They don't go away. Detectability versus quality, especially in low-entropy text. Robustness versus security, that's spoofing vulnerability, and making things more robust often increases the complexity and computational overhead of embedding and detection.
What about just the practicalities of rolling this out everywhere?
Big challenges there. We already talked about low-entropy text being hard. Short texts are another big one, often just not enough words to get a reliable statistical signal without a high risk of false positives or negatives.
And things like translation.
Major hurdle. Most current statistical watermarks are quite fragile to translation or very heavy editing that changes the linguistic structure significantly. Then you have the huge ecosystem challenges. Scalability is one. How do you implement this across thousands of different models? Standardization is another, getting everyone to agree on methods, key management, detection protocols. That's a massive coordination effort. Maybe something like the C2PA standard for image provenance could emerge, but for text.
That's a tall order. And what about open source models? That seems like a spanner in the works.
It's a huge challenge for universal enforcement, definitely. If a company controls their model API, they can enforce watermarking. But with open source models, users can often just modify the code, disable the watermarking part, or fine-tune the model in ways that might disrupt it. You can't easily force everyone using an open source model to keep the watermark active.
So watermarking can't be the only solution if open source is big.
It seems unlikely to be a universal, foolproof solution on its own for that reason. Its effectiveness might be higher in closed ecosystems.
So it really sounds like the tech itself is only part of the story.
Absolutely. The sources really emphasize this. The real-world success of statistical watermarking isn't just about having the cleverest algorithm. It depends critically on the whole ecosystem around it, meaning widespread adoption by AI developers, building reliable and accessible detection tools and infrastructure, having sensible policies and maybe legal frameworks around its use, making sure users understand what watermarks are and aren't, and just generally making attacks harder and more costly to carry out. A perfect watermark that nobody uses or that can't be easily detected is, well, useless.
Okay, this has been a really thorough deep dive. Let's try to sum up the key points. Statistical watermarking, it's this clever technique, embedding hidden signals by subtly biasing the AI's word choices as it writes.
Right, totally different from just sticking invisible characters in. Methods like KGW use those green-red lists and bias, while others like SynthID use more complex scoring and this tournament sampling idea.
And detection needs statistics. You need the algorithm, you need the key, and you're looking for patterns that are unlikely to be random chance.
Exactly, but there's this constant arms race going on. Attacks, especially paraphrasing, are a real threat. They can significantly weaken the signal.
Though maybe not without impacting quality, despite what some tools claim.
Often, yeah. And then you have more targeted scrubbing attacks trying to reverse engineer the watermark. And that really nasty spoofing problem where robustness actually creates a vulnerability.
So the future is likely about making watermarks even tougher, especially for tricky stuff like factual text or short snippets.
That, and pushing for standardization, better detection tools, and maybe combining watermarking with other methods for tracking where content comes from a layered approach.
Which brings us to the final thought, really. Something for you, the listener, to chew on. The ultimate impact of AI text watermarking isn't just going to be decided by the cleverness of the code.
Right. It really hinges on how the entire ecosystem responds. How do the AI labs implement it? How do platforms use detection? What rules do policymakers set? And how aware and discerning do we all become as users?
It's not the magic bullet, perhaps, but it seems like a really crucial piece of the puzzle for navigating trust and transparency as AI becomes even more woven into our lives.